Everyone's always asking me, Alamander, will you please make us a tuto rail in Arduino? Okay. If you can only do one project to start in robotics, you should build your own servo. Alex, what is a servo? That's a good question. They come in all shapes and sizes. Most of them spin, though a lot of cheaper ones have an angle limit. However, there is something they share that sets them all apart from a normal motor. If you've used one, you'll know that they're controllable. You can tell them where to go, as opposed to a DC motor just spinning endlessly whenever you provide it power. Well, what if I told you you could turn any motor into a servo motor? And for a clever roboticist, this opens up a lot of doors. You can make almost anything a robot. Yeah, that could be you. But if you still need some more convincing, this is why every roboticist should learn how to build a servo. Well, first of all, the components used to make a servo are going to be everywhere you look. Encoders, motors, microcontrollers, this is the bread and butter of robotics. Secondly, servos themselves are just everywhere, especially in complex robots, and it'll help you be able to choose the right ones for your project or work with them whenever you know how they work fundamentally. Lastly, it's a simple project to start with, but can grow in complexity as you grow as an engineer. As a bonus, it's one of those projects you can use immediately. I was talking with some friends who are just getting into robotics, and it reminded me of whenever I was first starting and I wanted to build this Arduino robot car. It was like one of the first projects I tried to make on my own, and I found a lot of stuff like this online that came with an Arduino, and even had a tuto rail, telling you what to do. And I watched a lot and read a lot of these tuto rails. And it was always like either in like camp A, where it was like steps 1, 2, 3, and then you didn't really understand what you did, but you had something, or it'd be camp B with like the theory mumbo jumbo, and I had a hard time understanding how to apply that into the real world. So I thought, why not combine them into something that makes everybody ask why? Stark gets it, don't you, buddy? A quick note before we get started. Most projects are going to have 4 groups of parts. Some brains or computation, like these microcontrollers, an actuator, which is just something that moves, some kind of way to tell what's going on, a sensor, and then some way to power the system. So keep these categories in mind as we go over the specific parts that we're using. I really try to choose parts for this tutorial that you could find in a makerspace, and if you couldn't find them, that they would be pretty easy to get wherever you buy your electronic goodies. And I also tried to make sure that I chose parts that should be fairly robust. You should have a lot of tries. So let's go over the specific parts. We're going to use the Arduino Uno because it's invincible. You can't really fault it. There's a reason that everyone starts with these things. This is the MX1508, which is just one of the newer motor drivers, or motor controllers, whatever you want to call it. It gives power to the motor. And you might find these older ones laying around. They work functionally the same. This is the AS5600. It's just, it's an encoder. It uses this magnet to detect the angle that our motor is on, and we can glue our magnet to the motor to make sure that we can detect how it's rotating. I'm choosing a 2-cell LiPo battery for this, and they come in a lot of different sizes, but what's important is that it goes into this buck regulator. It doesn't really matter what regulator you use as long as it outputs 5 volts. I chose this one because it has a USB output, which is kind of nice. But let's rewind and let's go over specifically what each of these parts does. And maybe more importantly, what each of these parts does in relation to the others in this design, and how you could switch them out or change them if you wanted to. Fun fact, every Arduino Uno that's ever been created still exists, because they're immortal. You're gonna do some just heinous things to these poor microcontrollers, but don't worry, the Uno can take it. You could throw this thing into the fire of Mordor, and he would come out on the other side, unscathed, still running the Blinky sketch on pin number 7. Okay, jokes aside, back to work. What you need to know about the Arduino in this type of project is that not all the pins do the same things. There are some pins that have this little squiggle on them, and those are the ones that we're connecting to our motor driver. Well, what do those squiggles mean, and why don't we use the other pins? The squiggles mean that those pins can do pulse width modulation, And we don't use the other pins because we need pulse width modulation. Easy enough. It's usually shortened to PWM, but whatever you call it, all you need to know is that it is able to be in between fully on and fully off, which is convenient because we want our motor to spin somewhere between fully off and fully on. If these are topics that you've never heard of before, you might want to go do like the Arduino Uno Blinky tutorial. But for now, we're going to move on to the rest of the system. And I think the next big building block that needs to be explained is the power to the system. In short, if you have a battery or a power supply that's between 7 and 12 volts, and you can physically connect it to your project, you're good to go. If you want to learn a little bit more, listen up. Now, we could have a whole video just on powering different robotic systems, but the quick and dirty is that you need to be thinking about 3 main things. The total energy in the system, like the battery's capacity. Number 2 is how well can your battery deliver that energy. For example, LiPo batteries are well known for how quickly they can deliver energy. However, it comes with the trade-off of not being as efficient at storing energy for the same weight of battery. The third item I'll put on this list is that you need to think about the format that this is in. Like what voltage is the battery and how much does it change over time? We call that voltage swing. This is a little example chart that I made about LiPo batteries, but this is going to be different depending on the chemistry of the battery. And physically, how are you connecting this to your system? Which seems like a silly question to ask until you're the one sitting there playing operation on your LiPo battery. By the way, if you ever have to do that, do not cut both the wires at the same time. You will short the battery and potentially weld your tools together and/or make the battery explode. If that was too much battery talk, don't worry about it. Almost any power supply that you choose for this project will be adequate. Maybe we should add a little bit more caution there and say, don't use your USB ports on your computers for powering projects unless you have a firm grasp on how much power you're drawing. Speaking of drawing power, here's a drawing of a voltage regulator I made. Technically, you can use the Arduino Uno's onboard voltage regulator. It is linear, which means that it just burns off the extra volts that you give it, which is fine for most applications. But if you do want your project to last a long time on a smaller battery, then you might want to look at a switching voltage regulator. Any voltage regulator that you choose is basically going to have an input and an output, and it might have a potentiometer or knob to adjust what voltage the output is going to be. And that's it, you're a pro. Let's move on. Future editing mode Alex here, realizing that I made a mistake. I stepped the voltage down too far in my project. Technically, the Arduino takes only 6 to 12 volts into the barrel jack. I fed it 5, which makes the microcontroller run at 3.8, according to my handy dandy multimeter. It probably slows down the Arduino, but I'm not pushing the limits of the computation here. So anyways, just to show that the Arduino Uno is very forgiving and you can make mistakes and your project might be fine. Though I guess running under voltage is a lot better than running over voltage. Motor controller time. These are the most fun part of the circuit. You're going to tell them what to do with your Arduino or your microcontroller, and they are going to do all of the hard work of channeling the battery power into the motor. The secret is that this little chip has a circuit called a half bridge inside of it. It looks like this. And with just the 2 input pins that we have per motor, we can control whether or not it's going to spin clockwise or counterclockwise. It's really important to point out how different this is than most people's first encounter with an Arduino. The blinky sketch and maybe some small sensors are fine to be powered by the pins of an Arduino. But there's a whole lot of fun things in the world of robotics that are going to need driving circuits to feed them power. Back to the big sheet, we have the motor. This one's simple. You give it juice and it gives you spin. Good talk. But when you add an encoder, that's what's really going to allow us to turn this into a servo. You can get the position that the encoder is reading 2 different ways with this particular chip. Maybe the simplest will be to just use the out pin and read it like a potentiometer. which just means that the voltage you read on the pin is linearly correlated to the angle that the chip sees. Your second option is to hook up the SDA and SCL lines to the Arduino A5 and A4 pins, which will let you use the wire interface and let you just ask the encoder what its position is. And congrats, you literally know everything now. Just throw it all together, glue a magnet on, toss that thing in a box, and you are good to go and ready to start programming. We're gonna walk through this line by line. Here we are, here I am, here we go. First things first, before we get started, you notice that we are using the AS5600, that's the name of our encoder. We're using a library that someone else wrote so that we can talk to it. Remember, with the wire interface? And to use that code that someone else does, we have to go to the manage libraries, and we have to add that library into our Arduino guy. The Arduino IDE will do this for you. All you have to do is open up the library manager, wait for it to update its indexes, and then go here in the search bar, and we're going to search AS5600. Probably you will have to click this button. All right, good talk. Now, this is the exact same code that we have in the Arduino IDE. I just copied it over to VS Code so that we can look at it with some nicer colors. If everyone's so scared of the beginning of Arduino files, you don't have to be. Include these two .h files. All that means is I'm just bringing in some other people's code. I didn't write the AS5600 or the wire library. I'm using their library, so it should be there. It should be fine. Next, we're going to define some just quality of life variables, or these are macros really, and that way we don't have to worry about like trying to remember like, oh, what pin did I connect to in 1 and 2 and blah 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 blah. This is just how you use the AS5600 library. We're creating an instance of the encoder here, and from then on we can just type AS5600 and it'll know that we're talking to the encoder on the wire interface. So then, before we get into the rest of this, let's talk about what we're doing with the rest of the code. First, we're setting up the Arduino for running as a servo, and we're just going to be driving the motor towards the set point that we're deciding. We're going to check the current position. We're going to calculate the desired motor output to get us closer to that position. And we're going to tell the motor controller what to do with that calculation. And then we're going to repeat, rinse and repeat. So there's one global variable that we need. We're going to need to remember what set point we're going towards. So let's make a global variable, set point. And then let's talk about our setup loop. Just talking about this block here. First up, you all know about pin modes. We're going to set up the pin mode in 1, in 2, and we're going to set them to outputs because we are outputting on them. Then we're going to make a serial logger so that we can talk to the thing, and you can use whatever baud rate you're comfortable with. And then we're going to copy this code straight from, all of these lines are just straight from the AS5600 examples. And then I'm going to wait a second just to make sure everything has time to do whatever and stuff. Okay, that was pretty easy, right? Everyone with me? Now let's talk about the loop. Again, all we're doing is checking the current position. That's number 2 on the list. So here we have a variable that we're creating, and we're going to check the position with the read angle function. I'm going to print it out just so that I know that, hey, the encoder's working. I recommend you start with this. Make sure that your circuit's put together correctly. Then we need to calculate the desired motor output. Okay, so we're going to calculate the difference. How far are we from the set point? We're going to set up another variable for power, and we're going to decide what power should be. How strong should the motor be spinning, depending on how far apart we are. If the difference is close enough, it's within 2%, 5%, I don't know, whatever percent you want to choose, don't do anything. Set the power to 0. Otherwise, let's set the power scaled to how big the difference is. So if the difference is big, we want the power to be maximum. If the difference is 0 is low, then we want the difference to be very low. 4096 minus the set point, because that is the maximum value. So from 0, which is the minimum value, to the maximum value, which is 4096 minus our set point, all the way, we're going to scale this to 40, which is the minimum value that it takes for the motor to spin, all the way to 255, which is the biggest number that we can send to the motor controller. Okay, so that's how I'm scaling the power. You can use your own algorithm, make whatever you want, as long as if the difference gets bigger, the power gets bigger, you're good to go. Now the next part, we need to tell the motor controller what to do, and we need to make sure it's in the right direction. So I just set up a little if-else block here, and we say if the difference is positive, let's spin this way. We're gonna hold in 1 down to low, and then we send the PWM with the analog write function, the power that we calculated, we're gonna send that to the other gate. And if we want to spin the opposite direction, we do the exact opposite. And that is like the simplest thing. This is called a proportional controller. And if you want to learn more about controls, that's a bit out of scope for this video, but it's definitely related to servos, and you should check out how to maybe implement a PI controller or a PID controller, and you could learn a whole lot. And this is where the coding for this project could really get more exciting. Anyways, I think this is a great place to stop. And good luck, everyone.
Wow, wait, that's a really cool way to make a knob.
Yeah.
You put the encoder on one side and the magnet. Oh wait, I guess that's what we do.
That is what we do. This was my first tutorial I've ever made. Let me know what parts of it you think weren't perfect, because I know that this thing was not perfect. I didn't know it was going to be so hard to pack a lot of information inside to this little video, because I was like, man, I'm glad I didn't choose a complex topic. Please let me know what you'd like to learn. And if it's something that I or someone I know can help us put together one of these videos on, I would love to do that. All that to say, thank you, and catch you next time.
Fushigi.